Okay, you'll have to wait, as I mentioned, one more weekend for the test grades. I'm running behind. I promise I won't do that next time. Wow, maybe I shouldn't make promises like that, but I won't. Um, so, but you may not have to wait a whole weekend because as soon as I get them graded, I will post them, and then I will send you an email saying the grades are posted. So you might be able to see your grade before Monday, if not the actual exam itself. All right. So the answers are already posted, as I already mentioned last time, on the Blackboard page under that test answers link. So that's where the test answers will always be posted. I'm waiting till I grade the test to update your calculus flux. So that's not been updated for a little while. But that'll happen simultaneously to the test, so you'll have a better idea of what your flux dollars are at this point. So for some of you, that total is going to change dramatically because you'll have extra credit dollars and then also hopefully a high test score to add dollars into your calculus flux totals. So this homework on integrating using the inverse trig functions, that's listed as being due today, right? So so I will adjust that a little bit. I'm going to move it back till tomorrow, but not too much, okay? So I'll give you through tomorrow night to finish this. So if you haven't made much progress on that, you have a little bit more time. Once you get into it, I think you'll be able to do the problems okay. And then this differential equations homework is listed for Monday, but probably have to adjust that due date. But we're going to finish talking about differential equations today, and then hopefully go on to the next section. So you'll be in good shape for working on this through the weekend, even if it's not, even if it ends up not being due Monday. So so that's where we are with the homework assignment. Remember, we're doing applications of integration now, so we're not going to learn any more new integration techniques for the time being. We'll come back to that and learn some more later. But now we're just going to apply the things that we've already learned, okay? And in particular with this first topic of differential equations, right? Of which we solved maybe one last time, and we were in the middle of solving a second differential equation when we ran out of time last time. So we'll finish that example today, and then look at some other examples of solving differential equations. Okay, so that's where we are with the homework, right? I wanted to look at this homework because I was just checking to see how difficult it is. Don't forget now you've got some links to some videos, and I think one of these at least there's a video for it, but we did this problem in class anyway, okay? But one of these, it may be example 4. One of those videos is really helpful for one of the harder problems here on the homework, which is this one, okay? So you'll have to check those videos and see which one looks like this problem, but there is one that looks like this problem. Now, they do give you a hint on this problem. They tell you you're going to do it by substitution, and here's what you're going to substitute, okay? So you're going to substitute a u for square root of x minus 9, but even with that hint, it's still there's still some steps involved in finding that antiderivative. So find the video there. I think it's the last one in that list. And look at that video because it will help you see what the steps are really for solving this particular problem. Oh, I think there's a video like this one too, but we did an example like this in class last time. Okay, this is one that's going to involve completing the square. You're going to complete the square on the minus x squared minus 8x, but because the sign there is negative, remember you're going to factor out that minus sign first before you try completing the square. So look at that example in the notes. It looks like this one from last time. Okay, if you get stuck on this problem. I wanted to also, the last two problems we didn't really do anything like this in the notes, but so let's talk about these. So they're not asking you to actually find these antiderivatives, but they're just asking you, do you know a technique at this point for finding this antiderivative, right? Okay, so can you think of one of the techniques that we've used, right, that could help us find this antiderivative, okay? And so let's go through that and see if we can recognize what technique we want to use here. If we know a technique, if we don't know a technique, then the answer would be, I don't know how to do this one, right? Okay, using the basic integration techniques that we've learned so far. Okay, that doesn't mean it doesn't have an antiderivative. In fact, all of these integrals will have antiderivatives, but just means that you may not know the tools for finding that antiderivative yet. Let's look at this one. So what technique do you think you can apply to finding an antiderivative for that expression? What arcsine, right? Yeah, sure. Arcsine will help us with this one, right? Okay, because that is the reciprocal of the square root, right? Okay, and the square root has that nice form, right? It's 1 minus an expression squared. So indeed, we can use arcsine here. Okay. What about this one, on the other hand? What now? So do you think that one we can do that one or not do that one, or what's your thinking about that? That's not arcsine, all right? Okay, it's not arcsine because what's wrong? What keeps that from the arcsine being useful? What? Yeah, the x in the numerator, right, is keeping the arcsine from being useful. But that x is helpful, okay? So you can make use of this x, but with a different technique. So any suggestions there of what we could try there? No, not arcsecant, okay? So it won't be arcsecant. If it was going to be, I don't think it's going to be arcsecant, right? Okay. For arcsecant, you would need this reversed, correct? Right? Okay. Remember, it's the expression squared first minus the constant squared if you're going to use arcsecant. So not arcsecant. Any ideas there? Just try using. You could just try using substitution. Okay. So why? Let me do something I don't often do, but let me write on the board here. Why would substitution be helpful or possibly helpful for this antiderivative? Okay. And we don't have to go through the whole substitution process to see what's going to happen here. So we have x over square root of 1 minus x squared, right? And since inverse trig function is not going to work here, then we don't have many other choices except maybe to try substitution. So let's try substitution. What do y'all want to substitute for? What seems like the natural candidate here? Well, the denominator, but I'm not going to do the whole denominator here, okay? I'm only going to look at what's under the radical, so just the 1 minus x squared, all right? So I'm going to let u be 1 minus x squared, okay? Now, that's going to work out really nicely because look what du dx turns out to be. Negative 2x, that's right, okay? And that's almost what we have here, right? Okay, except we have the x. That's the key thing, right? But we don't have minus 2, all right? But remember, the constant is not that crucial usually, right? Okay, the constant we can usually deal with by, factoring something out of the integral, right? So if you do substitute here, let's see, this means what? Dx is equal to du over minus 2x, right? So if you do substitute here, you would end up with x over square root of u, and then times du over minus 2x, right? And then just what you want happens, right? The x's cancel, and this is minus 1/2, right? But you can factor that in front. So you end up with minus 1/2 antiderivative of u, du, I mean, over square root of u, and that you can rewrite as u to the minus 1/2 power du, okay, right? Square root means 1/2 power, but this is in the denominator, so we can pull it up to the numerator by making the sign of the exponent negative. But this you can integrate using what basic integration rule? Anti-power rule, right. That you can integrate using the anti-power rule. So ultimately, it takes a little substitution first, right? But ultimately, you'll be able to handle this one using the anti-power rule, okay? This one now looks like you want to use the, this one looks like you want to use arcsecant, right? Because you have x, right? And then that expression squared, right? So remember, when you have expression squared and then the x, the expression outside of the radical, right? That usually means arcsecant, but you have an issue here. What's the issue? To use arcsecant, what's got to be the format of that quantity under the square root? The x squared has to be in front, right? Okay, remember, to use arcsecant, you need expression squared minus constant squared. For arcsine, it's constant squared minus expression squared. This is backwards, so I think that's going to mess us up, all right? So I'm not sure that we can integrate this one using basic integration techniques, okay? That's really close, but I'm thinking that one may be a lot more trouble than it appears, all right? That's what I think, okay? All right. Well, the next problem is very similar, but it's actually a little bit easier to think about, all right? So these are all exponential functions, or variations on exponential functions. So which of these do you think you can integrate? What about e to the x squared? Doesn't look that bad, okay? But are we going to be able to integrate that as an exponential function? Right, because it's easy to integrate exponential functions, right? They sort of, the antiderivative is sort of the same as the function, right? Okay, so but what's the problem with this particular integrand? Okay, all right. So someone needs to offer something for me here, right? What is the rule for what's the rule there for, as it's expressed in the book, right, for integrating, or in the notes, for integrating exponential functions? You can integrate if you have e to what? Doesn't have to be a number. It can be what? An expression, right? But what's got to be multiplied in there? The derivative of the expression, right, okay? The derivative of the expression. So this you can integrate, okay? E to an expression, u doesn't have to be just plain x. It can be an expression involving x, as long as you have the derivative of the expression. Then this integrates as e to the u, okay? Just that simple. But you've got to have this format. Does that match this form? You do have e to an expression, but what do we need multiplied there also? The derivative of the expression. What's the derivative of x squared, though? 2x. Not here, right? Okay? The 2x is not there. So if you try using substitution, which is what you would try here, right? You would substitute u for x squared. You're going to get stuck, all right? You're not going to be able to do this one. So this one we cannot integrate, all right? But this is vastly different because what is multiplied here? X, right? It's not quite 2x, but again, remember the 2 is not going to be an issue, right? Okay, the constant's not going to be an issue. So this one we're going to be able to integrate, okay, by substitution, but not this one. What about here? Same idea all over again, right? Okay, so you have e to an expression, right? 1 over x. So what do I need multiplied there to integrate that? The derivative of the expression. Well, what's the derivative of 1 over x? Let's check that. If it comes out something like 1 over x squared, I'm in great shape, right? So we want to check what is the derivative of 1 over x, all right? Well, what do you have to do with that to compute its derivative? Rewrite that how? The x on top, right? So if you wrote the x in the numerator, then what will the power be? -1, right? So 1 over x is the same as x to the -1. Now you can, we're not integrating. Be careful, right? Okay, we're checking the derivative here. So how do you differentiate this? What rule? Power rule, right? Okay, not the anti-power rule, but the power rule. So that would be what? Minus x to what? The -2 power, which by the way is -1 over x squared. Yay! That's right there, right? Okay, exactly what we need, except the minus sign is not there. But again, that's just a constant. So that's not really crucial to us, right? So, so yes, we can integrate this one. So these two we will be able to, but this one so far, we won't, all right? Based on what we know now. Are we ever able to integrate, Taylor? Can we integrate that one?
No, you can't.
Yeah, that was really hard, right? Okay. Right. Okay. Right. So Taylor said that one's even harder than it first appears. Okay. All right. Okay. So those are those last two problems. That's what they were. That's what those problems were getting at. So that's really important skill. So because on a test, right? The skill that we're practicing in these problems is really important skill because on a test, you know, especially the further we get along in the course, right, you're going to have an antiderivative and, you know, you're going to have to be thinking of how do I approach this antiderivative, and you'll have a lot of techniques to use, right, okay, and so you need to be thinking about, you know, how do I recognize which technique is the one that I want to apply to this problem, so you're not, you know, just staring at the problem for 15 minutes on the test and then wasting all your time, right, okay, while you're taking the test. Or, you know, maybe it's a problem you can't even do, right, okay, so you don't want to be wasting your time trying to, you know, do something that, you know, you don't even know how to do, right? Okay. Do y'all have other questions from that homework yet that y'all want to ask? Have y'all been, did they ask questions in your session? Oh, okay, good. All right. So, so Taylor's been doing these. If you're able to visit Taylor, right, in her tutoring sessions, I know a lot of y'all have been going, so that's good. Okay. All right. So much for homework. Let's go back to our notes and let's finish up this example. We need to review it really because I'm gonna forget what we were doing at the end of class last time. We were just trying to solve this differential equation, right? So remember, that's a differential equation because it's an equation and it involves the variables x and y. You don't see x, but it's there implicitly. And derivatives of y, okay? And the reason I see, there's the derivative of y, right? And then there's the variable y. Now, we don't have x in this equation, at least you can't see it, but it is there invisible, all right? Because remember, in differential equations, you're thinking of y as being a function of x, right? So keep that in mind, right? Y equals f of x. Y is a function of x. That's an assumption we're making in solving these differential equations. So that being the case, see, I can take the y prime and I can rewrite that using the old-fashioned notation for derivatives, dy over dx. And see, there's the x now appearing, right? Okay. Since y is a function of x, we can differentiate y with respect to x. That's what y prime means, right? Okay. And rewriting that y prime in this old-fashioned notation is really useful in solving differential equations. Well, in particular, this differential equation. Okay. So if you rewrite y prime as dy over dx, you have dy over dx minus 2y equal 0. So remember, what we're looking for is the value of y, but the value of y is not going to be a number, it's going to be a function, right? A function of x. So we're looking for what expression, right? Okay, for y can we substitute into this equation and make it true, right? So you're not going to get numerical solutions to differential equations. Your solutions are actually functions, okay? And that sometimes it takes a little while for students to wrap their head around. That's kind of a conceptual leap, right? Solutions to our equations are not numbers because you've been dealing with, you know, solutions to equations as being numbers since, I don't know, whenever you started solving equations. Where do people learn how to solve equations now? Kindergarten? Okay, well, all right, since kindergarten, okay. I think it was probably maybe 7th grade or 8th grade before I saw an equation. All right. Well, anyway, wherever. You've been doing it. You've been using that idea for a long time, right, that solutions to equations are numbers. So, but this is a little bit more sophisticated idea. Solutions to these differential equations are actually functions. They're not numbers. All right. So we rewrote the y prime here as dy over dx. And then the technique that we're going to use on these examples that we're going to be practicing with in class, because we're just using this as an application of our integration skills. So we're really not here intend on studying differential equations because that's a big topic. So in the technique we're going to use for solving these differential equations, what I want to do is I want to separate the variables. What I mean is I want all the x's on one side of the equation and all the y's on the other side of the equation. And if we can achieve that, then it turns out that usually it's pretty easy to solve the differential equation. So here's what I'm going to do. Let's take the, what am I going to do here now? I'm trying to split the x's and y's. So I moved the 2y over to the, I moved the minus 2y over to the right-hand side, okay? And then multiplied both sides by dx, right? And then divided both sides by y. So those are the three steps. And I ended up with, originally, just that dy over y is equal to 2 times dx. The integral signs weren't there yet, okay? Right? So I had dy over y is equal to 2 times dx. So notice the variables are separated, right? All the y's are on the left-hand side, and the x's, well, there's only that dx is the only quantity that involves x, right? But anyway, the x's are on the right-hand side of the equation. And now, what we're going to do is integrate, because the dy over y and 2dx, those look like integrands, correct? Okay, so we're going to attach integrals to both sides of the equation. We're going to integrate both sides of the equation. And we know how to do that now because we've learned a lot about integration. So we know that dy over y, that integrates as natural log of y, correct? Okay, we learned that on like the first day of the class, right? Okay, actually natural log of the absolute value of y. Don't forget there's a constant here though, right? And then, of course, 2dx, that's a simple integral, right? That integrates as just 2x, right? Plus, don't forget there's a constant here though. And these two constants do not have to be the same. So that's why I put subscripts on them, just to indicate that they really don't have to, strictly speaking, have to be the same number there, okay? All right, well, that's where we were last time. But we're not finished, okay? Because I've got to solve this equation now for y, right? Okay, I've got to get y equal to some expression. And that is the solution to my differential equation. So I've got to continue doing some algebra here. But from now on, this is really just algebra. The calculus is kind of gone, right? Because I've integrated both sides and the dx's and the dy's are gone. So now I just have an algebraic equation that I can solve for the variable y, okay? All right, so now you get to apply some of your, your algebra skills that you learned in your past classes, right? To solve this equation for y. Let's see, let's take the C1 and let's move that over to the, so you may proceed a little bit different way, there's more than one way sometimes to solve equations, but let's take the C1 and let's move it over to the right-hand side, right? Okay, so I'll get natural log of y is equal to 2x plus C2 minus C1. So 2x plus C2 minus C1, but here's what I want to point out. Remember, these are just constants, correct? These are just numbers, and they're numbers that you can make up, okay? This is an arbitrary constant, and this is an arbitrary constant also. So when you add, well, in this case, when you subtract two constants, you're going to get another what? Constant, right? Okay, you're just going to get another constant. So rather than writing two separate constants here, I'm just going to combine them now, and let's just call them C, okay? I don't need to put I could put C3, I guess, because that's now a new constant, but I don't have any other C's in the equation, so I'm just going to call this this subtraction, let's just call that C. So I have natural log of absolute value of y is equal to 2x plus C, okay? All right, now y'all have to help me because I've got to solve for y. So how do I solve for y here? That's right, okay. You're going to apply the inverse, right, of the log to both sides, right? And the inverse of the log is exponential function. So you're going to take both sides of, you're going to raise e to both sides of this equation, correct? And when you do that, right, the e and the log cancel, right? So you have absolute value of y is equal to e to the 2x plus c. Now, here's the part that you have to sort of see someone do, although it's just algebra. I claim that e to the 2x plus c is the same as e to the 2x times e to the c. Why is that? So why are these two right-hand sides the same thing? Well, remember, when you multiply powers that have the same base, what do you do with the exponents? You add them. So if you take e to the 2x times e to the c, these powers have the same base, then you would just add the exponents, right? So see, these two things really are the same. Now, the advantage to this, the advantage to rewriting like this is, look, e is a constant, this is a constant, so when you take a constant and raise it to a constant, guess what you're going to get? Another what? Yeah, this is just a number. It doesn't involve variables, okay? So I don't have to write that down as e to the c power. I'm just going to say that's a constant, okay? That's some other constant, so I'll just call that c, okay? That's now a constant. So here we have absolute value of y is c e to the 2x. We're getting really close. There is kind of my formula for there's kind of my formula for the y, right? See, this is a function of x. By the way, what sort of function of x is that? What's the name for this type of function? Exponential, right? That is an exponential function. So notice here, y is going to be an exponential function. So the solution to our differential equation is an exponential function. But the one other ugly thing here is I don't have just y, I have absolute value of y. Okay, so I want to get rid of the absolute value because that's just ugly, right? Okay, well, let's see. If the absolute value of y is equal to this, all y does is change minus to positive, right? So that means that y could have been either plus or minus c times e to the 2x, right? Okay. See, if the absolute value of y is this, that means y could have been either plus c e to the 2x, right, or minus c e to the 2x. So we can use that reasoning to get rid of the absolute value. Now, one further simplification here. So here you have plus or minus a constant. But plus or minus a constant, that's just a constant, right? Okay? Because the constant itself could be chosen as negative. So you don't have to write plus or minus a constant, all right? You can just replace that with one single constant. The constant could be plus or the constant could be negative. So you really don't need to write plus or minus here. That is redundant because c already is just a constant. So you can take that off of your solution and there you're done, okay? There's the solution to our differential equation, right? Okay? So any function that looks like this, right? Any function that looks like this is a solution to this differential equation. Let's see, so what are some examples of functions that look like this? So y could be what? It could be 3e to the 2x, right? Okay. There I just picked a value for c, right? C to be 3. Or it could be 1/2 e to the 2x, right? Okay. Because there I just picked a different constant. Or it could be 0.1 e to the 2x, right? Okay. There I just picked a different constant. All of these functions are examples of solutions to this differential equation. There are a lot of solutions to this differential equation, and you get new ones just by picking different constants here to use as a coefficient. All right. So that's it. There's the solution to the actually it's solutions because there's lots of them, right? Okay. Every time you change this number, you get a different solution to the differential equation, but all the solutions have this format. All right. Okay. So there's a couple of examples of solving differential equations. Hang on to this example because we're going to use the logic from this example again, actually several times. Okay, all right. In particular, starting right now, All right, so let's look at this. This is kind of an applied example, kind of, not super applied, but all right. So here we're told that we have this quantity y. So think of y as being a function, all right, and so the rate of change of this y is directly proportional to y itself, all right? All right, so there's some terminology we have to remember, okay? Directly proportional, all right? But then we have some more information here. So when it says so apparently this quantity y is changing over time, right? Okay, and it says when time is of t equals 0, y is 2. But when the time goes up to 2, so I don't know if this is minutes or seconds or months. It doesn't really matter here what the units of measure are for the time, okay? But when the time goes up to 2, then y changes to 4. What we want to know is how much is y when t is 3, okay? So I kind of drew a little picture of just what we were told here, right? Oops, I used the wrong variable though on this axis. This should be t, right? So all they told us here, right, is when t is 0, y is 2, and when no, is that right? Yeah, when t is 0, y is 2, right? Okay, and when t goes up to 4, y has gone up to when t goes up to 2, y has gone up to what? 4, right? Okay, and now what we want to know is what is y when t is 3? So what is y when t makes it to 3? Okay, so clearly y is increasing, right? I mean, that seems pretty obvious, right? But exactly what does y move up to, okay, when t goes to 3? Right? There's a lot of mistakes you can make in this problem, okay, if you don't think about it properly. But let's go back and we got to remember this terminology here. What does directly proportional mean? Okay, so when one quantity is directly proportional to another, what is that telling you? Okay, so if you're told that the quantity y is directly proportional to the quantity t, just as a for example here, if you were told the quantity y is directly proportional to the quantity t, do you remember what that means? This often comes up in science classes, okay? Because in science classes, you frequently have quantities that are directly proportional to other quantities, okay? So you might hear this terminology a lot in science classes, but you also hear it in math classes as well, okay? All right, so if you say that the quantity y is directly proportional to the quantity t, okay, what that means is those two quantities are related, but by a very simple type of function, very, very easy type of function, okay? Here's what the function would look like, all right? So the function would look like this, very easy function, all right? And k here is just a number. It's just a constant. This, by the way, usually is called the constant of proportionality. So you want to remember this easy terminology, okay? Again, if you say the quantity y is directly proportional to the quantity t, that means they're related here, right, by just very easy type of function, okay? That means y is just some number times t, okay? By the way, what type of function is that? What category of function is that? That's called a proportion function, by the way, but more generally, what sort of function is that? If you graph this thing, what are you going to get? A line, right. Yeah, this is a linear function, okay? It's a linear function. You know it's a linear function because it has degree what? What's the degree of this function? Remember, t is the variable, the input variable here. So what's the degree of the function? 1, right, okay? Remember, functions whose formulas have degree 1, those are linear functions, okay? All right. So another name for k, besides constant of proportionality, would be what? In a linear function, what would you call that number besides this? Slope, right, yeah, okay. So k is also the slope of this easy linear function, all right? Okay, now, so let's go back now and read what the problem said, because the problem did not say the quantity y is proportional to time, right? Okay, what did it say? Okay, it said, it didn't even say the quantity y, it said what? The rate of change of the quantity y is directly proportional to what? Not t, but to what? Yeah, y itself. Ooh, okay, that sounds weird, all right? Now, you couldn't say the quantity y is directly proportional to the quantity y, because that's kind of stupid, right? Okay? But this doesn't say the quantity y is directly proportional to the quantity y. This says the rate of change of the quantity y is directly proportional to not the rate of change, but the quantity y, okay? So let's see if we can take those words and write them down as an equation, all right? So how do you write rate of change of the quantity y? What now? Yeah, so how do you write down the derivative of y? Let's use old-fashioned technique here. Dy over, but we don't have x's here. What's the dt, right? Okay, so dy over dt is equal to, it's directly proportional to what? Yeah, it's directly proportional to y, right? Okay, so that means that this rate of change is some constant of proportionality times y, okay? The rate of change of y is directly proportional to y itself, all right? That's what that first sentence is telling you. Ooh, what is that thing now? So what did we just learn to call this? Well, it's got an equal mark in it, so that makes it what? Statements with equal marks are called what? Equations. And this equation has a what in it? What's that? Derivative. So what sort of equation do you have here? You have a differential equation, right? Okay. All right, so we have a differential equation, right? Okay. And what we're going to try to do is solve that differential equation, okay? That's our goal here. So see where we've arrived here at a differential equation, okay? So that one sentence, that one simple sentence there gives us a differential equation. Lots of quantities now. It turns out in practice, especially in science, lots of quantities have this property, okay? The rate of change of the quantity is proportional to the quantity itself. Lots of examples in science of the quantities that you study in science have that property, okay? So this, we're going to see some examples of that in just a second, specific examples of that in just a second. So this type of situation can occur frequently, okay, in practice, all right? This is a very abstract example of that, but again, we're going to look at some specific cases of that in just a second. All right, so we want to try to solve that differential equation, okay? Now, you may be wondering, well, how am I going to use the extra information? Well, we'll get to that, all right, how that extra information is going to be helpful to us in just a moment. But our first task there is to solve that differential equation. Now, I want to point out, look, it's very easy to write this differential equation down incorrectly. If you leave off the y, you will get this differential equation, okay? That's still a differential equation, by the way, all right? Still has y's in it and x's in it, right? Okay? And derivatives, okay? So that's still a differential equation. What is that differential equation saying? In words, what is the situation that that differential equation is describing? Here, you're saying that the derivative of y is just what? Just constant, right. The derivative of y is a constant. So that means that the rate of change of y never changes, right, okay? It's always the same number. What sort of functions have that property? Linear, right, okay? Linear functions have constant rates of change. What is that constant rate of change, of course, known as? No, they don't have to be 0, but you can have lines with rate of change 0. That would give you a horizontal line, right? Okay, but not all lines are horizontal. Okay, but someone said it here. What? Slope, right? Yeah. Okay. The constant rate of change of a line is called the slope of the line, right? Okay. So what this is telling you, what this differential equation is telling you, right, is you have a line and the slope is what? Constant, right? Okay, it's this number k. All right. So if you write this formula down wrong, if you write this differential equation down wrong from this information, you're going to solve this differential equation, and you're going to end up with a straight line. Okay. Now, what would we know about that straight line? When t is 0, what? Y is 2, and when t is 2, what? So you're going to think this picture, if you're working from this differential equation, you're going to think this picture of the graph of y looks like what? A straight line, right, that goes through these 2 points, correct? Okay, so you're thinking, see, this differential equation means I just have a straight line, and the straight line goes through these 2 points, and so now it'd be really easy to figure out what the value of y is when t is 3. Okay, can we just project that? Let's see, what's the slope of this line? What is the slope of that line? Nope. 1, right, okay. The slope of that line is 1, right, okay? Right, okay. You're going up when t goes up by 2 units, right? How much is y going up by? Also 2 units, right? So that means the slope is 1, all right? So when t gets to 3, what would y be? 5, right, okay. So you're thinking, yay, I'm done. I know the answer here, right, okay. I'm done, right? The answer is 5, and I'll go on to the next problem, but you're wrong, right, okay, because you wrote the differential equation down wrong, all right. You made a wrong assumption, it turns out, about what this line looks like. Now, there is a curve for the function y, okay, but the curve is not going to be a straight line, okay, because there are lots of ways to connect these 2 points with a curve, right, okay, and straight line is not it, okay, all right. This differential equation, it turns out, is not going to give you a straight line, okay. It will give us, of course, a nice curve connecting those 2 points, but it ain't going to be a straight line. So this answer is going to turn out to be wrong, all right. I wonder, so let's erase this curve, because this is the wrong curve. I wonder what this curve really does look like. You know, it could be concave up, right? Like this, right? Okay. So if it's concave up, that means when you get to 3 here, you're going to be at a lot more than 5, right? Okay. So see, 5 maybe not the right answer. Or, what's the other possible concavity you could have there? Could be like this, right? Okay. And that means when you get to 3, y is not going to be up at 5, okay? But we don't know yet what that curve really does look like. So we have to solve this differential equation, okay? All right, now, when you start solving the differential equation, you're not going to know what this constant is, so you have to be prepared to solve the differential equation. You have to keep that variable k in your solution. So don't get nervous about working and solving the differential equation with the variable k there. But remember, k represents a constant, right? Y is a variable, t is a variable, but in this problem, k is fixed. We just don't know what its fixed value is yet, all right? Okay, so let's start solving this differential equation. And now y'all know what to do, because this is actually very similar to the differential equation we just solved a moment ago, okay? So what do we do first? Yeah, so we want all the y's on one side, and we want all the what? The t's, right, okay. T is the other variable, right? So how would y'all accomplish that? So you want to do what first? Someone suggested something. So to get dy over y, what did you do? Oh, so you're doing two steps at once. So let's take them one step at a time. What was the first step there? Multiply by dt. Okay. All right. So multiply both sides by dt. All right. So I'll do that first. Multiply both sides by dt. So I get dy is ky times dt, right? Now what? Divide by y? Great. So I get dy over y is k there times dt. Now I'm in great shape, right? See, the variables are separated. Remember, this is not a variable. The variables are separated. So now what? Not differentiate. Yeah, I really should smack you for saying differentiation, right? Okay, because I warned y'all about that. Integral, right, okay? Integrate, not differentiate, right, okay? So, again, be careful when you're, the difference between integration and differentiation, right? So, you're integrating here, right? Basically, why are you integrating? What are you trying to get rid of? Not the t's, right? What are we trying to get rid of? Yeah, the dy and the dt. By the way, what are those called? Those are rates of change, right? Okay, so we want to get rid of these derivatives, correct, right? Okay, how do you get rid of derivatives? You integrate, right, okay? You integrate, okay? So we're integrating to get rid of the derivatives, right? So let's see, actually those are not called derivatives, but but the idea is correct, all right? So what's the antiderivative on the left-hand side? Yeah. Just like in the previous example, right? It's natural log of absolute value of y is equal to, and what is the antiderivative here? Oops, I almost, t. Not just t, but what? kt, right? Okay. Don't forget now, you've got some constants, though, right, that you can add on. Be careful about adding on the constants. They're going to be needed later, all right? And these are not necessarily the same constants, but we're going to combine them soon here, so they really essentially will boil down to one constant. Now, here's one thing I can do really quickly, all right? Notice here, fortunately, our values for y are, see, y is increasing, right? So our value for, and it starts off at 2, so our values for y are positive. So you can drop the absolute value bars, okay? So really quickly, you can drop the absolute value bars, so that's nice. So just write natural log of y there, and then let's move the c1 to the right at the same time. So I get k times t plus c2 minus c1, and what am I going to do here now? Combine them, right? So I don't need to express those as two different constants, right? So I'll just write those as one constant. Now, how do we eliminate the natural log? E, right, okay? So raise e to both sides of that equation, and then on what happens nicely on the left-hand side, you just get y, and on the right-hand side, I have e to the kt plus this constant. Now I'm going to split that up. That's e to the k times t times e to the c, because remember, when you're multiplying powers that have the same base, you add the exponents, but e to the c is just what? That's just a constant, right, okay? So just replace that now also with constant. So there is your function, all right? There is the function. It's not a linear function, right, okay? Y is not a linear function, right? It is an exponential function, okay? So when you graph that, you don't get a straight line. You're going to get a curve, right, okay? So those 2 points, 0 and 2 and 2 and 4, they're supposed to be connected with a curve. But now we have to figure out exactly the correct formula for this curve. Otherwise, I'm not going to be able to predict the value of y when t is 3. So I got to figure out what is the right value for this c and what is the constant of proportionality, okay? All right, so how do we do that? You do that by substitution. So you want to make use of the information that you were given here, all right? So one key piece of information we're told here is that when t is 0, y is 2. So there's your formula, right? If you kind of erase the middle there, there's your formula. Y equals c e to the k times t. And when you know when t is 0, when you plug 0 in for t, what pops out for y? 2. So let's put that in. And let's see what that tells us. So we have 2 is equal to c. This is c, not e. This is c e to the k times 0. Oh, that's so nice, because what's k times 0? What's e to the 0? 1, not 0. E to the 0 is 1. So you just get what? What's c? 2. Okay? So now you know what c is. So we're halfway there. Now we just have to figure out what is k. Okay? All right, well, that's where the other piece of information we can use, right? Okay, so we know, let's see, oh, by the way, we know c is 2 now, right? So we can plug 2 in for c. And we know when t is 4, y turns out, no, I'm sorry. When t is 2, y turns out to be 4, right? So I have it backwards there. When t is 2, y turns out to be 4. So now I have an equation with one unknown, k, and I can solve for k. All right, so let's solve that equation for k. Let me see if I have enough room here to do this. So first I would divide both sides by 2 to get rid of this 2. So when you divide both sides by 2, you get 2 is e to the 2 times k. K times 2, I wrote it as 2 times k. And now how do you solve that equation? What do you do here? Natural log of both sides, right? Okay, so you have natural log of 2 is equal to, when you apply natural log to the right-hand side, the e will cancel, so you'll just get 2k. So there's our answer for k. K is the natural log of 2 divided by 2. How much is that approximately? So this is where your calculator will help you. All right, give me a few decimal places there. What is natural log of 2 divided by 2? What? 0. What? 35. Have some more decimal places there? 35 what? Oh, 0.347. Let's try 4. So 0.347 what? 66. All right, thanks. So 3466. Now you've got it, right? There's your function. 2e to the 0.3466 times t. And now we just want to know, okay, what's the value for y when t is 3, all right? So what's the value for y when t is 3? So plug 3 in there. So you have 0.3466 times 3, raise e to that, and then multiply for me. And what do we end up with? So 5.65 what? All right, so 5 point. Now I'll let you round off to a couple of decimal places. So it's 66. All right, so there's our approximate value for y when t is 3, 5.66. So So what does this curve really look like? Which of these two is the right curve here? Concave up, right? Okay. This so here's the more like the graph of that function that's described here. Okay. Because it goes up a little bit more than 5, right? Okay. The linear function would give you exactly 5 when t is 3, but we're a little bit more than 5, so this curve is concave up, right? Like that. Ooh, all right, so there's kind of our first application, right, of differential equation. All right, so we want to see another better application, and so we're going to look at, when we come back, we'll take a little break here, and when we're going to come back, we're going to solve almost exactly the same differential equation. So you're going to know sort of, even before you even start, what the solution to the differential equation looks like. This differential equation has to do with, radioactive decay. Radioactive plutonium, I think. Okay, all right, specifically. So, so we'll look at that in just a minute, all right? Okay, now let's resume. All right, so so here we're going to solve a very similar differential equation to the last two examples, but again, this is in a lot more applied setting, so you get a feel for how these differential equations really are, really can manifest themselves in practice here. So here we're given that 10 grams of plutonium isotope were released in a nuclear accident, right? Okay, so that's the bad thing about nuclear accidents, right? They tend to release radioactive material. So, in this case, it's plutonium, and so you know, radioactive substances, right? Like plutonium, they decay over time, right? So they dissipate over time because the nuclei of these radioactive substances is not stable. So the nuclei dissolve, and then these protons and neutrons, right, that are forming the nuclei of these atoms in this radioactive substance, they fly off in all directions, right? Okay, and so so over time, slowly the radioactive substance dissolves, right? And you don't want to be around the radioactive substance, right, when it's dissolving. It depends a little bit about how fast the radioactive substance is decaying as to how dangerous it is to you. But in general, you don't want to be near these radioactive substances because these subatomic particles, even though they're quite small, right? These protons and neutrons that are flying off, right, when the radioactive substance dissipates, those are going to interact with your genes, and they will damage your cells. Okay, and so then you tend to develop radioactive sickness or cancer, right, ultimately, from being near these radioactive substances. So that's why we don't want them released, right, into the environment in nuclear accidents. All right, so for now, what we're given here is that plutonium has a half-life of 24,100 years. So that means that it takes a long time, 24,100 years, for a sample of plutonium to decay by 1/2. All right, that sounds like a really slow decay rate. Okay, that's a long time to decay by 1/2, but that's fast enough to kill you if you are around that plutonium even for a short period of time. Okay. All right, so but what we want to know here, though, is how long will it take if there initially 10 grams of this plutonium gets released? How long would it take for that 10 grams to dissipate to 1 gram? Okay, all right. Given that it takes 24,100 years for half of it to decay, how long would it take for this initial 10 grams to decay to 1 gram? All right. So let's set up some variables here. So obviously what we're interested in is measuring the amount of plutonium, right? So I'm going to call that Y in the problem. We're not giving any suggestions about what to call these quantities in the problem, but I'm going to let Y be the amount of plutonium and present. Let's say amount of plutonium remaining from that initial 10 grams, right? And let's let T here be elapsed time. So that means we're measuring time from, when the nuclear accident occurred, right, and released the plutonium. And let's see, the amount of plutonium, clearly that's measured in grams, right? So I better write that down in case we need to refer to that. And elapsed time, let's measure that in years because we're given information about the half-life in years, right? So might as well be consistent and let measure elapsed time in years. All right, now here's what I didn't tell you, okay? But this is absolutely crucial to answering this question. All right, so you know what the half-life of plutonium is, but you need to know also what the rate of decay of the plutonium is, correct? Right? Okay. So at what rate is this quantity Y changing? It's decreasing because the plutonium is decaying. But what do we know about the rate of change of Y? Well, for radioactive substances, conveniently it turns out that the rate of change of the substance is proportional to the amount of substance remaining. All right, that's a key principle from science. All right, so that fact allows us to write down a differential equation. Right. Again, the rate of change of a radioactive substance, right? So that in this case, our plutonium, that rate of change dy over dt is proportional to the amount of the substance remaining, all right? So dy over dt is equal to some constant of proportionality, right, times the amount of the substance that's there, right, which we said is y, okay? So look what we ended up with there. We ended up with a very similar differential equation to our previous two examples, right? We have a quantity that is proportional to, the rate of change of a quantity that's proportional to the quantity, okay? So I think now we could repeat the steps of solving this differential equation, but we've practiced that twice, and I think you already know from our previous two examples what the solution is going to end up looking like, right? Okay? Because we're starting with exactly the same differential equation as in the previous two examples, all right? So I'm going to skip that part of solving this differential equation, separating the variables and integrating, because we've already practiced that twice for this type of differential equation. And you know then that after you go through those solution steps, what is ultimately your solution to your differential equation going to look like? What is it? C, right? Okay, times E what? T, right? Okay, it's this differential equation isn't that exactly the same as the one in the prior example, right? Okay, so when you solve that in the prior example, where did we get it there? Right there, right? Okay, that was the solution to the differential equation we got. So when we solve this differential equation, we're going to get the same solution, correct? Okay. Now, what's going to be different, though, in this problem, of course, is that value for C is going to change, okay, and that constant of proportionality is going to change, all right? So we do have to figure out what, in this problem, what the C is, and also what the constant of proportionality is, okay? All right, so let's do that, all right? Okay, so how do we figure out what the C and the K are? Well, here you have to use now some information that you're given, right? Okay, so we know that at time 0, right, that is when the plutonium is first released, correct? We know that the amount is what? So what is the initial amount of plutonium there? 10, right, okay? So see, you know from that description of the problem, see, you know when T is equal to 0, right, when the nuclear accident first occurs, right, Y is equal to 10. The amount of plutonium is 10. So you can plug that into your function now, right? So we know Y is 10 when T is 0. Well, what's K times 0? That's 0, right? And what's e to the 0th? 1. So you end up here with C on the right-hand side. So C is what? 10, right? So we know now what the value for C is, right, in our formula. C is 10. By the way, this illustrates really well some terminology. This constant here in this function, this is often called the initial value of the function. And you can, so in an exponential function, this coefficient, this is an exponential function. So in an exponential function, if you have a coefficient in front of the e, that is often referred to as the initial value for the exponential function. And you see where that terminology comes about, right? Because what's the initial plutonium amount in this problem? 10, right, okay? The initial value for the amount of plutonium is 10. Let me write that down just to have it in the notes. So again, this constant C is often called the initial value. Of course, this constant K is the constant of proportionality, right? Okay, we already have a name for that. All right, so we know what C is. Now we got to figure out what K is. All right, so what information can I use to figure out what K is? That's where the half-life is really helpful, okay? Because we know that if you plug in for T this number, 24,100, what are you going to get for the amount remaining? 5, right, because the half-life of plutonium is 24,100, right? So if you start with 10 grams, after 24,100 years, you're supposed to get down to 5 years, all right? 5 grams. So let's do that then. So I know that 5 is equal to C, but I know what C is, right? That's 10. E to the K times, let's see, what is that T value that gives us that? 24,100. So now we have to solve this equation for K. There's only one variable left in this equation, right? E is not a variable, right? So, so let's solve this. So what do we do first to solve this equation? Yeah, we got to get rid of the 10. How do we get rid of the 10? Divide. Yeah, divide both sides by 10. Well, what obviously happens here is you get 1/2, right? See? Half-life, right? So 1/2 is equal to e to the 24,100 times K. And now, what do I do next? Natural log, right? So I get natural log of 1/2 is equal to, and when you apply natural log to the right-hand side, it'll cancel the e, so you get 24,100 times K. And there is the value for K. Really strange number. It's natural log of 1/2 over 24,100. By the way, if you want to, you don't have to, but you can write, how can you rewrite natural log of 1/2? That's natural log of a quotient. So how can you simplify that? Minus natural log of 2, right? Remember when you have natural log of a quotient, you can turn it into a subtraction, right? And what is natural log of 1? 0. So I really have here minus the natural log of 2 over 24,100, okay? Notice that the K turns out to be negative. This is a negative number, so K turns out to be negative. That makes sense because the amount of plutonium is decreasing, right? The amount of plutonium is decreasing, not increasing here, okay? All right, so, well, what is minus the natural log of 2 over 24,100? So you really need your calculator to help you with that, right? What's that approximately? There's what now? 4 zeros? 0, 0, 0, 0, and a 2, and a what? And a 2, 8, 7, 6. All right. I just want to write down lots of decimal places so we can get lots of accuracy there in our final answer, because we're not to the final answer, right? Okay. All right. So, well, all right. So there is our constant of proportionality. See, that is negative. So notice that if you plug that into the differential equation, the k is negative, right? So that means your derivative is negative. But when derivative is negative, that means the quantity is doing what? Decreasing, right? Yeah, but that's what plutonium does, right? It decreases. It's not increasing, right? Okay, it's a radioactive substance. Okay, wow, where am I going to write down my final formula here with that big decimal value there? So here's my formula for y. Y is equal to, what was c? 10, and then e to this number, right? Minus 0.00002876 times t. Well, not that bad, okay? So there's the formula for our solution to our differential equation, okay? It's a little bit of an approximation because this is really a decimal approximation for k. But essentially, right, that's the solution for your differential equation. All right, now, finally, how do we use the solution to get at the answer? What were we trying to? I forgot the question. What were we trying to discover here? How long it takes for what? Yeah, for what to equal 1? Y, right? Okay, yeah, for the amount to equal 1. So just plug 1 into that solution, right, and solve that equation. Well, y'all can do that now really fast. Did y'all do that good on the test? You had equations like this on the test. Did you solve them? No? Oh, my God. Okay. Well, I mean, we're solving equations like this a lot. So, all right, well, you're going to get some more practice. All right, so y'all know how to do this, right? What do I do first? Divide by 10, right? Okay. So divide both sides by 10. Let me do that without rewriting this equation. So when I divide by 10, this is going to be 0.1, right? Okay. And then do what? Yeah. So I have natural log of 0.1 is equal to minus all of this, right? 0.0002876 times t, and now just divide by that minus 0.2876, right? I'm not going to write that twice, so there's our final value for t there. It's natural log of 0.1 divided by minus 0.00002876. Whew. Okay. Someone want to tell me approximately what that number is? You can round off to the nearest year. What now? 80,000 exactly?
No,
80,062? 80,062. That? Okay. All right. So it takes a little while there, right? Okay. For the plutonium to get down to 1 gram. That's why. See, this is why disposal of waste from nuclear plants, right, is such an issue, because it takes a long time for the radioactive substances in that waste from nuclear plants to decay, right? Okay, thousands and thousands of years, and so that makes it very difficult to find a place to store that stuff, right? Because you got to store it in a really safe place where, you know, it can hang around for a long, long time without getting disturbed, right? So that's one of the big problems with nuclear energy, is figuring out what to do with the spent fuel, right, from the nuclear energy from the nuclear plants, because that stuff is radioactive. All right, there's a video example for this one, but I want to, show you just the start of this. So when you go to the differential equations homework, this is solved completely, this example. But I do want to show you the start because it has a little bit of a trick in it, okay? All right, so this is another example of a type of quantity that where the rate of change is often proportional to the quantity. It's populations under ideal conditions. So that means lots of resources, right, to feed the population, and lots of space for the population to grow. So an experimental population of fruit flies has 100 flies after 2 days, and of course they're multiplying. So it's up to 300 after 4 days, and we want to know then what was the initial population, okay? So what was the initial population? See, you're not told the initial population here, right? You're just told that after 2 days you had 100, okay? And then after 4 days you had 300, but you don't know how many fruit flies you started with at first, right? So that's what we're trying to figure out, okay? All right, so again, let's set up some variables here. Obviously, we're interested in what quantity in particular. So what should be my y in this example? What's the main quantity we're measuring here? The population, right, yeah. So everything revolves around the population, right? So we'll let y be this experimental population. And so for our input variable, again, we're observing that population over time, right? So our input variable here will be elapsed time. The fruit fly population is just, that's just measured by counting, so that really doesn't have a unit of measure. Let's see, elapsed time, I guess, is measured in days, right? In this problem. All right, so again, the key thing that's missing from the problem that I have to tell you, or you have to learn somehow, is the fact that populations, the rate of change of populations is proportional to the amount of population that you have. Okay, all right. So that's an important fact from biology. All right, that's under ideal conditions. So if you write that down as a differential equation, see, from biology we know that the rate of change of the population is proportional to the amount of the population. Okay, that makes sense, right? The more population you have, the faster the population is growing, right? Because you've got more population to breed, correct, right? Okay, to reproduce. So that differential equation kind of intuitively makes sense, right? Bigger population, faster rate of change of the population. Okay. All right. So see, notice we're right back to a similar differential equation that we've solved now already 3 times, right? Okay. But we do need to solve that differential equation to have a chance at answering this question. But what's the solution going to look like? So we already know, right? Y is going to end up being what? C what? E to the k times t, right? Okay. And C is going to end up being your initial value, right? So that's your initial population, but unfortunately, that's what you're looking for, right? You don't know what the initial population is, right? Okay. And of course, k there is your constant of proportionality. Well, we don't know that to start with either. Okay. All right, but what do we know? Well, we do know have a little bit of information. So let's apply that information. So that first thing, let's see, we have 100 flies after 2 days. So if you plug those values into your solution to your differential equation, you have 100 is equal to what? C e to the k times 2, right? And then you also know that there's 300 after 4 days, right? So you have 300 is equal to C e to the k times 4. And you just got to figure out what's the C. That's actually what we're asked for here, right? And but then incidentally we'll also have to figure out what is the k, what's the constant of proportionality. So we've got to figure out what these two unknowns are. Now, fortunately, we've got two unknowns that we're trying to figure out, c and k, but we're lucky here we have two equations to find those two unknowns. And usually if you have a collection of unknowns that you're looking for, you need as many equations as you have unknowns. So since we have two unknowns here, we need two equations, but we're in great shape because we do have two different equations, right? The question is, though, how am I going to use those two equations to figure out what c and k are? All right, I'm going to show you a trick here. This involves a trick. This is why I wanted to show you this. All right. If you didn't see if someone did demonstrate for you, you might have a hard time using this trick. Okay. Here's what I'm going to do. I'm going to divide one equation by the other. All right, so I'm going to divide the left-hand sides and the right-hand sides. Let me take 300 over 100 so I don't get a fraction that way. All right, and then I will divide c e to the, this is 4k, right, over c e to the 2k. So look what happens on the left-hand side. Of course, that just turns out to be 3. Now, what happens on the right-hand side? A nice thing happens here too, right? What happens to the c's? They cancel, right? Okay, so the c's cancel, and you end up with e to the 4k over e to the 2k. But here you're dividing powers that have the same base. So when you divide, not multiply, but when you divide powers that have the same base, what can you do with the exponents? Subtract, right? Okay, so so this is really e to the 4k minus 2k, which is 2k. So look, now you've got this equation, 3 is equal to e to the 2k. And can you solve that? Yeah, right, okay. Just by doing what? Natural log, right? Applying natural log to both sides. So you can figure out what k is, see, then take that. Once you figure out the value for k, now take that and plug it back in to either one of these equations, and you'll be able to figure out what c is. And then that's the answer to the problem, because we want to know what is the initial population, right? Okay, so once you get your solution for k here, you got to get a number, right? So it may have to be a decimal value. Take that, plug it back into one of these two equations, and then you can figure out the value for c, okay? All right, so again, that is on video tape, right? So if in your homework you have a problem, you know, one of these differential equations, and they're asking you what's the initial value, but they don't, you know, give you information about the initial value, then remember this example, okay, because it may be useful. I want to show y'all one more application, okay? Now, this is a very famous one. Is used a lot, all right, in physics, and this is Newton's law of cooling. So have y'all ever seen, you know, one of these crime shows where someone has been murdered, right? And they're trying to determine the time of death. So they have lots of, so when the murder occurred, right? And so there's lots of, you know, work that goes into that sort of estimate. But if the death is relatively recent, okay, relatively recent. So if then they can sometimes estimate the time of death by measuring the temperature of the corpse, right? Okay, it won't have completely cooled off from 98.6, right, or whatever our normal body temperature is, right? So they can measure the temperature of the corpse, and then they can get an estimate for how long the person's been dead, right? And to do that, they use Newton's law of cooling, okay? All right, so that's just one application of Newton's law of cooling. It's very important in physics. All right, so what Newton's law of cooling says is, so this is the same Isaac Newton from calculus, says the rate of change in the temperature of an object is, so this could be an object that's cooling or actually heating up. It also applies to heating as well. So the rate of change in temperature of an object is directly proportional to the difference between the object's temperature and the surrounding medium. Okay. All right. So imagine that you've taken a hot object, right? Okay, and you've placed it into a room, right? So the room has a surrounding temperature, correct? Right? Okay. So what Newton's law of cooling says is that it tells you information about how fast that object is going to cool off to the temperature of the room, right? Okay, the surrounding temperature. So it says that's going to cool off, and the rate that it's going to cool off is, again, directly proportional not to the temperature of the room, but to the difference between the object's temperature and the temperature of the room. Okay, right? So it's a little bit slightly more complicated situation than our earlier examples, all right? It also applies for heating. So if you take, for instance, frozen pizza and you put it into an oven, okay, of course it's going to heat up to the temperature of the oven, right, eventually. But the rate of change at which it heats is proportional to the difference in the temperature between the pizza and the oven, okay? All right. So notice what that means is that for instance, for the pizza in the oven, as it gets warmer and warmer, right, as it gets closer to the temperature of the oven, it won't be heating up as fast, okay, right? At first, it heats up really rapidly, okay, but as it gets closer to the temperature of the oven, it doesn't heat up as quickly. It's continuing to heat up, but not as rapidly. All right, so let's apply this to an example, and let's at least see if we can get the differential equation written down and see if we can think about how we're going to solve that differential equation. All right, so I don't have much of a good story to go with this one, but it just says the temperature Y of an object is initially 100 degrees. Well, that's close to body temperature, right? So is initially 100 degrees. It's placed in a room that's kept at a constant 60 degrees, okay? So the surrounding temperature is 60. Of course, the object is going to cool off eventually, right, to the 60 degrees, right? And so we're told, okay, the object cools off to 90 degrees in 10 minutes. How long will it take to get down to 80 degrees, right? So eventually it's going to go down to 80 degrees. Eventually it's going to go all the way down to 60 degrees, right? But how long will it take to get to 80 degrees if it takes this long? 10 minutes to get to 90 degrees. Now, if you're not paying attention in class, you're going to tell me what? You're going to answer this in a naive way, and you're going to say, okay, to get to 80 degrees, that will take what? How would a school child approach this? They would just say what? What? Say it? 20, yeah, right, okay. The naive answer would be, 20 minutes, right? Okay, because it took 10 minutes to cool off 10 degrees, so it'll take another 10 minutes to cool off another 10 degrees, right? Okay, so the answer altogether is 20 minutes. Well, all right, I guess not a bad guess, right? But what are you assuming implicitly in that when you make that guess? That's right, that the rate of cooling is constant, right, okay? It's cooling off at the same rate in the first 10 minutes, in the second 10 minutes that it did in the first 10 minutes, right? But that's not how cooling works, right, okay? Because as the object gets closer to the temperature of the room, the surrounding temperature, right, what happens to the rate of change of the temperature? It's going to slow down, okay? That rate of change of that temperature is proportional to the difference between the object's temperature and the surrounding temperature, okay? So it's not a linear rate of change, all right? So that's one of Newton's many contributions, right, to physics, okay, is this law of cooling. All right, let's see if we can write down the differential equation. So we've got to write down some variables. So, well, some of them are already here, right? Y is the temperature, right, of the object. So, so that's easy. And let's see, of course, we're measuring that temperature after a given amount of time, right? So, so we're back to elapsed time, correct? So let's let t be elapsed time here. And that's measured, I guess, in minutes, right? So elapsed time is measured in, oh, by the way, the temperature of the object, of course, is what? In, yeah, it doesn't say if that's centigrade or Fahrenheit, right? Okay, let's go with Fahrenheit. Doesn't really matter. All right, now, so there's our variables. Now we have to write down the differential equation, okay? Because we're told something about a rate of change, right? So that information that we're given about rate of change, we're going to translate that into a differential equation, right? So we're told the rate of change of the object, right? That's Newton's law of cooling, all right? The rate of change of the object. So the rate of change of the temperature here, right? How do you write that? Yeah, that's dy over dt, right? Is proportional to, so what does that translate to? K, right? Is proportional to, and then it's K times something, right? And that thing is, what we told in Newton's law of cooling, it's the difference between the and the surrounding medium, right? Okay, so what's our objects? How do we write that down? The difference between the object's temperature, right, and the surrounding medium. So how would you write that as an expression? Yeah, y subtract 60, or you can write 60 minus y if you want to, okay? That's fine. You might as well write y minus 60, though. That may be a little bit more convenient to write it this way because this number is going to be positive, right? Always. If you write it as 60 minus y, you can still come up with the right solution, except this ends up being negative, and that makes things messy, maybe. All right. So there is there it is. Okay, there is the differential equation that we want to solve, and we're going to solve that, of course, by doing what? Well, integration ultimately, but before we do the integration, what we call that process, what I want to do to sort of clean up the equation. Yeah, move what? I'm going to move some things around. What's my goal? The variable separated, right? Okay, it's separation of variables. That's what I want to do. So I want to get all the y's on one side and all the, in this case, t's on the other side, right? That's pretty easy to do. Don't multiply this out, by the way, okay? Do not multiply that out. First multiply both sides by dt, right? So multiply both sides by dt. And then, so you get dy is equal to, k times y minus 60 times dt, right? And then divide by y minus 60 without multiplying out there. So you get, it looks very familiar, just slightly different, right, than what we had before. And now the variables are separated. Now what can you do? Integrate, right, okay? Now we can integrate. And boy, y'all can integrate this like crazy. What is the antiderivative on the left-hand side? Natural log of what? Y minus 60, yeah. And what's here? K times t, right, okay? See, when you integrate k times dt, you just get k times t. The d goes away. So don't forget, though, our constants, because they're going to be useful to us. So you have k times t and then plus this second constant, right? Okay? Now we're just going to solve this equation. So that is just algebra. By the way, what about the absolute values here? Not necessary, right? Because this temperature is always above what? 60, right? So you can immediately erase the absolute values. You're not really erasing, just replace them with parentheses, okay? So that's nice. And now you're on your way there to solving that differential equation. All right, well, we'll finish solving this up on Monday, but you can solve that one, okay? That's just now algebra. So if you run across a homework like this in your problem like this in your homework, you can get through the differential equation, okay, solution. All right, so I'll see y'all on Monday then, right? Okay, so be working on, I'm going to give you one extra day, but finish the integration by, inverse trig functions, right? Okay, finish that by tomorrow.